Okay, so let's start today's lecture. Okay, so now last time we have been talking about solving a differential equation. Okay, so in particular, there was such an example that we had last time. Is such an equation. Okay, so that last time we had such an equation that we were trying to solve. Okay, so and this is an equation that takes the form of dA over dt is 500 minus 0.4 of a. It was used to model the evolution of the amount of drug in the person's bloodstream. Okay, so and in order to solve this equation, we have been trying to integrate it. Okay, so that in this sense, solving a differential equation essentially amounts to how do you integrate the differential equation, right? So in order to integrate a differential equation, one has to kind of change the form of the representation form of the equation. It cannot be something like this, because if it is something like this, you directly integrate, then you're going to integrate something that you don't know. Okay, so in order to overcome this difficulty, we have been devising such a method that you can divide 500 minus 0.4 of a to both sides of this equation and separate. Okay, so and separate the variables t. Okay, so and separate the variable t with the unknown function a. Okay, so in this way, you're able to integrate the whole equation, and that during this integration process, we have seen such a phenomenon that there might be constants coming out, right? So when you find antiderivatives, you have constants coming out, and when the constants coming out from line to line, when you play with this equation, from line to line, these constants might vary, right? So this constant might vary. So this is a typical phenomenon that might happen, might occur in applying differential equations, is that the solution. So basically, we start from this equation, dA over dt, right? So it's this is equal to 500 minus 0.4 of a. This differential equation is going to give you a solution as a function of time. Okay, so a of t is equal to 1,000. Okay, so 1,250 minus some k times e power minus 0.4 of t. Okay, 0.4 of t. So that's the solution in terms of a function of time, right? So, but typically, what you really see, okay, what you really see is that this equation is a solution depends on the constant k, right? So it depends on the constant k. So what happens to here is that why the solution is depending on the constant k, right? So that's kind of give us such a quite confusing scenario. Why is that the case? Because your original problem, right? So if you look at the original problem, the problem is about the administration of the drug into the person's bloodstream, right? So that kind of raises this weird question, because if it is the case, right? So if it is the case that there is some k, then it means that for different numbers of k, the amount of drug in a person's bloodstream is going to be different, which is anti-intuitive, because the problem is natural. I mean, it's a problem from real world practice. That means the amount of drug in a person's bloodstream must be something that you know, right? So it cannot happen that the amount of drug in your person's bloodstream becomes something that is always changing, right? So it's a depends on constants. So that's kind of a problem with this example, right? So with this example, so in particular, for example, that you can see that here is a graph of the shape of this function at for different choices of k, right? So so for example, if I choose k to be 1,250 minus, right? So 1,250. So if you took this function, that will start from 2,500 and started to decrease as time increases. Okay. Now, if you take another k, for example, k is equal to 1250, then this function is going to be increasing from 0 up to a certain asymptote as t goes to infinity. So that's kind of gives you a very anti-intuitive phenomenon that the amount of drug in the person's bloodstream is actually changing, right? So it's actually changing with respect to the different choices of k. Is that the real case? Is that the real case? So this kind of calls upon these differences between general solution and specific solutions. Okay, so for ordinary differential equations, okay, for any ordinary differential equation, usually, okay, so usually when you use such an integrating method, like what we performed in the last lecture, when you use this integrating method, you're going to end up with a solution that involves this unknown constants k, right? So involve this unknown constants k. This is what we call it a general solution. Okay, so this is what we call it a general solution. Now, if your solutions are with respect to a certain different choices of k, then this is called specific solutions. How do you pass from general solution to specific solutions? Well, if you have general solution, then you must see that in practice, okay, think about the practical situation. If you're in a practical situation, the amount of drug, how do you determine the amount of drug in a person's bloodstream? Well, you have the equation for AT, that's good, but this is not enough. Why it is not enough? Because besides this equation for AT, you must also know, okay, so you must also know how much drug is present initially at the person's bloodstream. So that means you must know A of 0, which is 1250 minus k. That's A of 0. Only but for different choices of A of 0, the amount of drug in the person's bloodstream should be different. Why is that? Why I say it should be different? Because you can look at this picture. For example, if the amount of drug, because here the problem has a competitive phenomenon. Mechanism between two kinds of effects. One is that a person's the person's body tissue is kind of absorbing the blood. Absorbing the drug, right? So on the other hand, the drug is flowing into the person's bloodstream. So that's kind of, for example, if initially the person already has a lot of drug in his bloodstream, then you can see that consumption is going to take effect first. Dominant effect, and therefore the amount of drug is kind of decreasing because he's consuming it, right? So, and what happens here is that if initially the amount of drug in the person's bloodstream is 0, then it's flowing in, right? So the flowing in of the drug is going to take a dominant role, and you're going to have more and more amount of drug in the person's bloodstream. So that's kind of for different choices, initial conditions, situation is going to be different. In particular, it is worth mentioning that in our example on Monday, that we've been talking about how much of the drug is present in the bloodstream after a long time, right? So there has to be a steady state situation that everything went steady. And it is indeed the case because 1250 is going to be steady. If you start from 1250, the amount of drug never changes in your bloodstream, right? So that's kind of steady. And if you start from anywhere else, then you're going to have the asymptote, which is 1250. Okay, so it is possible to draw pictures, for example, like this, or maybe for different initial condition, they're always going to be have the asymptote, which is 1250. Okay, so that's kind of initial condition is very important. You must tell me what's the initial amount of drug from which you can see that there will be a constant k, which is 1250 minus the initial amount. As long as you have the k, you put it there, then you're going to get specific solutions. By specific solution, it means that this is a solution of this ordinary differential equation corresponding to the specific scenario, that you're not going to have this unknown constants. Okay, if you have this unknown constants, then the solution is called a general solution. Otherwise, it is called a specific solution. So that's kind of the way how you're going to work out these differences in differential equations. Okay, so that's the initial condition is very important for you to determine the specific solution. And you're able actually to read everything from the slope field. Okay, so you might be able to see if you draw the slope field, you will see that the amount of drug is decreasing when you're above 1,250 until you reach the asymptote, and it is increasing to 1,250 until you reach the asymptote if you're below, if your initial condition is below 1,250. So that you can see there's actually a phase transition between the asymptotics, the asymptotic monotonicity of the amount of drug in a person's bloodstream. And this physically is because of the competition between the two mechanisms that you're simultaneously consuming the drug as well as letting the drug flow into your system, a metabolic system. Okay, so that's kind of the from this example, we see this kind of very important notions such as general solution and specific solution and initial conditions, and these are going to play a very important role in later of our analysis. Okay, so that's kind of the to finish the first topic about solving these differential equations that we have been talking about on Wednesday and Monday. Okay, so now let me come to a very important theme. Okay, so let me come to a very important theme for today's lecture. Okay, so and I have to let you know that this is a very important theme that's going to occur in your upcoming exam. Okay, your exam 1. We're going to cover this topic. Okay, so this is a very important theme that you're going to be covered in your exam 1. That's called the classification of ordinary differential equations. Okay, so that's kind of, this is a very important topic. Okay, so classification of ordinary differential equations. Okay, so now how do you classify the ordinary differential equations? Well, there are actually criteria to classify ordinary differential equations. For example, here this first notion is called the order of an ordinary differential equation is the order of the highest derivative that appears in the equation. Okay, so in general, you can see that an ordinary differential equation or differential equation is like an envelope relating, for example, t is the variable and u of t is the function. Then an ODE typically takes the form that you're going to use an envelope to relate all the derivatives, right? So of u as well as the original variable to be equal to 0, right? So that's kind of a typical shape of an ordinary differential equation. Okay, a typical shape of an ordinary differential equation. Now you can see that the order, okay, so order of this ODE is going to be just equal to n, because n is the largest number of derivatives in your envelope equation. So the order is actually equal to the largest derivative that might occur in the differential equation. Okay, so the largest derivative that might occur in the differential equation. Okay, so that's kind of a very simple. This is very simple. Okay, so for example, let me give you some examples, right? So for example, if you take y prime, right? So y prime plus y is equal to t, for example, this is order is 1, right? So, but when you determine this order, so it is very important for you to understand that we have to specify which one is the function and which one is the variable. Although it is looks like here you're just looking for a function of t. So u is the function and t is the variable. So you're looking for a function u as a function of t. But in general, it might not be the case. For example, here you have to realize that you're looking for a function y as a function of t, right? Y equal to y of t. But it might also even be something like this: x double prime plus ax prime plus b of x is equal to y. If it is like this, then you must realize that it is looking for x as a function of y, right? So x is now the function and y is the variable. And so that's kind of the about the orders, right? So what's the order of this equation? Order is 2, right? So that's the order of differential equation. It's just the highest number of derivatives that might occur in this differential equation. Okay, so that's the order of a differential equation. Now I'm going to talk about a much more sophisticated notion, and we're going to practice quite a lot of exercises related to this notion for the rest of today's lecture. Okay, so So that's a kind of notion is called linear or nonlinear ordinary differential equations. Okay, linear or a nonlinear. Okay, so let's say the linear, let's generally say the linear. Okay, so the linear ordinary differential equations. Okay, so right, so what's a linear ODE? Well, a linear ODE must look like something like this. Okay, so it must be y to the power of derivative, the nth derivative, with a coefficient an of t, and then plus an minus 1 of t of y to the derivative n minus 1 plus dot 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 plus a1 of t y prime plus a0 of t of y is equal to, let's say, g of t, right? So that's a typical ordinary differential equation. That is a linear. Okay, so that's a linear. So let me ask you the question. Okay, so what's the order of this differential equation? What's the order of this ordinary differential equation? Anybody can give me an idea? Okay, so anybody can give me an idea? What's the order of this differential equation? You can either unmute yourself or you type in the chat, but it would be best you unmute yourself and you speak loudly. I'll be able to hear you. Can anyone tell me what's the order of this differential equation? Order? Any idea? Order? Any idea? Anyone has an idea? The order of this differential equation. Order is the highest number of derivatives that occur in the equation. So how do you determine the order? Well, the first thing is to ask yourself, which one is the function? Which one is the variable? Can you tell me which one is the function and which one is the variable? So we're looking for a function y as a function of t or t as a function of y. Any idea? Any idea? You can unmute yourself and then you can speak. Any idea? So we're looking for y in terms of t or t in terms of y. Anybody has idea? Okay, so we're looking for a function y in terms of t, right? So that's this is looking for a function y in terms of t. So therefore, this y is going to be the function and t is going to be the variable. So therefore, the order of this differential equation is just equal to n, because the largest number of derivatives that occur in this differential equation is n. Some people might ask, what happens to a0, a1, and an minus 1, ant? Well, these are functions of t, right? So these are explicitly given functions of t, including that g. These are explicitly given functions of t. They have nothing to do with the dependency of y in terms of t, right? So how do you determine which one is the function? Whichever every variable that's going to have that's going to have the derivatives are going to be play the role as the function in the differential equation, right? So that's kind of very important thing. Okay, so that's kind of very important thing that you must realize whenever you see a differential equation. Okay, so let me add this a small remark that please do not be shy to talk about anything in class. Okay, so sorry, so to raise any questions in class or when I ask you to actively participate in discussions of these exercises, like what's the order of this differential equation? You do not have to be shy to talk about it. Okay, so and let me also mention that on your Zoom, when you log into the Zoom system, on the lower left corner of your Zoom panel, there is a microphone like symbol and saying that mute or unmute. Okay, so whenever you enter the system, I have already muted everybody automatically, but you can click that symbol, then you'll be able to unmute yourself. And when you unmute yourself, when you speak, everybody can hear your voice. Okay, so otherwise, you can also type in the chat if you want to answer some of those questions. Okay, so this is kind of that's kind of kindly remind you about this Zoom functions. Okay, so now let us look at this differential equation and compare it with the envelope type differential equation like this. Why do we say this is a linear, right? So why do we say this is a linear differential equation? Well, we say this is a linear differential equation because of two reasons. First reason is that the coefficients. Okay, so if you look at this equation, we're going to say that the coefficients do not depend on any of those unknown functions as well as derivatives. So this here, it is very important for you to realize that which one is the function and which one is the variable. For example, here, y is the function and t is the variable, right? So y is the function, t is the variable. And therefore, the first thing is that the coefficients, right? So coefficients, that means coefficients a0, a1 up to an t do not depend. Okay, so do not depend on okay, so of course it depends on t, it depends on the variable, but it does not depend on any of those functions. So that does not depend on y prime, or any derivatives of this unknown function. So in that sense, we say it's linear because this linearity is actually linear with respect to y. So that means if you change this equation by y by 2y, then it's just multiply both equations by 2, but it's not going to change any of those coefficients. So that's one of the reasons why we say coefficients do not depend on y as well as y prime until y derivative. So that's one of the reasons why it is called linear, right? So, and what's the second reason? Well, the second reason says that it is linear in y as well as any of the derivatives of y. So that means you're not going to see, okay, so you're not going to see, for example, yn square, or maybe square root of yn. You're not going to see any of these terms in the differential equation. You're not going to see this, you're not going to see this, right? So you're not going to see any of those terms like this in your differential equation. And this is why. So that means the equation is linear in y and y prime as well as any derivatives of y, right? So you can see that these are all order 1 polynomials of any of those y's as well as its derivatives, right? So that's it's just a linear combination of any of those y's as well as derivative. You never see nonlinear functions in y. Okay, you never see nonlinear functions in y. So that's the second reason why I say it's linear in equation. Okay, so and about the third thing is about the right-hand side. Okay, so about the right-hand side. So in fact, by linear ordinary differential equation, it simply means that the coefficients and the functions are linear. Okay, so however, you must determine, for example, if gt is exactly 0. Okay, so suppose gt is exactly 0, then you can see this equation is ant y to derivative of n plus an minus 1 of t y to derivative of n minus 1 plus dot 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 plus a1 of t of y prime plus a0 of t of y is equal to 0, something like this. Now, if you have an equation like this, you're going to, let's say you multiply this 2 on both sides of this equation. So 2 times an of t, 2 times an minus 1 of t, right? So of y of n minus 1 plus dot 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 plus 2 times a1 of t of y prime plus 2 times a0 of t of y. It's going again to be equal to 0. So this equation is actually the same thing as the previous equation. It never changes, right? So this, in this sense, it means that if the right-hand side is equal to 0, then the equation is what we call it homogeneous. Okay, so homogeneous is like in chemistry, like you have a homogeneous material. That means the material is invariant under any scaling, right? So spatial scaling or dilation of this the spatial variable. So the homogeneous is really the case that no matter what you multiply to the equation, it never changes the essence of this equation. So that's called homogeneous. Now, in contrast, if the g of t is non-zero, then it's called non-homogeneous. Okay, so non-homogeneous. So there's a difference between homogeneous and non-homogeneous equations. Okay, so but you must realize that the notion of being homogeneous or non-homogeneous are pertinent to linear equations. Okay, so there's both are pertinent to linear equations, so that basically when you have linear equation, you can always classify it into homogeneous and non-homogeneous. Okay, so right, so you can always classify it into homogeneous or non-homogeneous equation depending on the right-hand side. So the homogeneous and is 0, the non-homogeneous is not 0. Okay, so and it is actually not very precise to say that is depending on the right-hand side of this equation. Why is that the case? Because the right-hand side is relative, right? So this is an equation. So you're able actually to remove everything that g of t, maybe back to the left-hand side. So it's not really the right-hand side or left-hand side. So how do you determine which one is the term that helps you to determine the homogeneous or non-homogeneous of this equation? Well, the key point is that the g of t is a term that is the only term that in this equation, it does not involve any of those y's. So you basically, you collect all these terms that involve the unknown function to the left-hand side of this equation, and the right-hand side equation is the term that do not involve any of those y's. If that term is 0, then it's a homogeneous equation. If it is non-zero, then it's a non-homogeneous equation. So this is how you determine homogeneous and non-homogeneous of these equations. Okay, so here we would like to, this is the typical instruction style of this class, is that we're going to work out a lot of exercises together. Okay, so we're going to work out a lot of exercises together. That's why I say you can unmute yourself and speak loudly when there is any, when we raise questions and ask you to participate. Let me remind you that this class is like a continuation of your calculus classes. That practice is the most important thing for you to do well in such a class. So therefore, I would strongly urge you to participate in the practice problems that we showed in class. And most of these problems are going to be taken from previous year's exams, so that presumably it will help you a lot in preparing for your exams if you participate the lectures regularly. Okay, so here is a very nice exercise, is to fill in all this, the whole table, right? So the first column of this table are some equations, and we ask you what's the order of this equation. Is it linear, non-linear? Is it homogeneous or non-homogeneous? Okay, so this is a very nice exercise. Let's look at this equation. So what should we do the first time we see equations? What should we do the first time we see equation? The first time you see an equation, the important thing that you should do is to determine which one is the function and which one is the variable. Okay, so can you tell me for this equation, is it y in terms of t or t in terms of y? Anybody has idea? You can unmute yourself and just speak loudly. Anyone has idea? Maybe I unmute everybody. So anyone has idea? Is it t in terms of y or y in terms of t? Anyone has idea? Right, so somebody says that in chat, right? So y in terms of t, yeah, you can, I have already unmuted everybody. So if you want to say something, you can just speak to your microphone, and then I will be able to hear you. Yes, thank you very much. You are the first person who has been answering questions in class, and I appreciate this a lot. Okay, I encourage everybody to, I mean, there are some difficulties of participating in this kind of discussions, especially in an online form, but I think Zoom has already given us a very good platform. Okay, so a very good platform to do this. Okay, so and let me remind you again that if you want to answer questions that I raised in class, just click the mute or unmute button on the lower left corner of your Zoom panel, and this will turn on your microphone, because I have already muted everybody in order to keep the class silent. But you can unmute yourself, and then when you speak, I'll be able to hear you. Okay, so or you can just type in the chat if you like to, but I would prefer the first method. Okay, don't be shy to answer any of those questions that we raised in class. We're going to have a lot of such exercises during our lectures. Okay, so yeah, you're right. So I would like to thank this thank you for answering this. That is y in terms of t. Once you have known that this is y in terms of t, then the order is determined to be 1 because the derivative of y, the highest derivative of y in this equation is just 1. Is this a linear or non-linear equation? Anybody has idea? How do you determine that? Well, in order to see whether or not it's linear or non-linear equation, one has to compare the equation with the given existing form of this linear equation, something like this, right? So that means you have to ask yourself 2 questions. What is the coefficient of y? If the coefficient does not depend on y, right? So it only depends on t, then you're done. And second question is that if you have this y's, are you going to see y square or y square root or anything like that? If you don't see anything like that, then it's linear, right? So that's kind of, you apply this to this equation, you see the coefficient in front of y prime is 1, so that's independent of t. Therefore, and you don't see y square or y prime square, anything like that, so that means this is a linear equation, right? So it's a linear equation, and is it homogeneous or non-homogeneous? Well, it is not a homogeneous equation because well, you can say that there is a non-zero right-hand side, but it's more precise to say that there is a non-zero term that do not involve any of those y's. I mean, I don't see y here, but this is a non-zero term, so that's a non-homogeneous equation. Okay. Now, what about the second equation? So, can anybody tell me, is it y in terms of t or t in terms of y? I expect it from you. Is it y in terms of t or t in terms of y about this equation? Can anybody tell me? Any idea? Is there anyone who's brave enough to say this?
Is it y in terms of t?
Right, so yeah, so thank you very much. I mean, for your braveness. I mean, you're the first person who really has voice in this lecture. Okay, so it's highly encouraged. Okay, it's highly encouraged. So it's right. So this is y in terms of t, right? So this, we're looking for a function y as a function of t. So therefore, you can see, in order to determine the order of this equation, it's just suffices to look at the highest derivative in y, which is 1. So the order must be equal to 1. Is it a linear or non-linear equation? How do we determine that? Well, you must look at the coefficients, right? So you must look at the coefficients in front of those y's, and you can see that, for example, if you have y prime, then the coefficient of y prime is already y, and this violates the principle because we want the coefficients to be independent of the unknown function, right? So, and that's why the first question is important. You must realize that this is y in terms of t. Right, so as long as you realize this, you're able to see that here, that means this is not a linear equation because your y prime, it has a coefficient y, which is independent, which is depending on y. So as long as it's a non-linear equation, when we ask you, is it homogeneous or non-homogeneous, you don't have to answer it. Okay, so you can just say no. Okay, so but it's more precise to say not applicable. But in any case, you don't have to worry about this. So you just say not applicable, right? So, and what about this equation? So let's be a little bit faster and faster. Okay, so what about this equation? Is it y in terms of t or t in terms of y? I expect again someone can answer it. Anybody has idea? Y in terms of t or t in terms of y? Don't be shy. Anyone has idea? Is it y in terms of t or t in terms of y? Anybody has idea?
Y in terms of t.
Right, so it's y in terms of t. Yes, thank you very much for answering this question. I really appreciate it. Okay, so it's y in terms of t, right? So therefore, y is the variable and t is the function. So y is the function, t is the variable, right? So therefore, in order to determine the order, you just want to look at the highest derivative in y, which is 3. So the order is 3. And is it linear or non-linear equation? Well, you look at the coefficients in front of y, the derivatives of y. And this coefficient is good, it's just 1. But this one is not good because you squared the third derivative. So that's a nonlinear equation. So this is no. And if it is nonlinear equation, as we said before, you can just say not applicable. An A for this equation, if it is ask you is homogeneous or non-homogeneous. So that's kind of nice, answer. Okay, so and I appreciate answering these questions raised from me. Okay, so and it's highly encouraged for the rest of the course. Okay, so let's practice this one. Okay, so is it y in terms of t, t in terms of y? Anybody has idea? I want a quick answer. Just do not be hesitate to answer the questions whenever it happens. Okay, so and just chat as usual. Okay, so don't be shy. I mean, is this y in terms of t, t in terms of y? Anybody has idea?
Y in terms of t.
Y in terms of t, right? So thank you very much. And indeed, this is function y in terms of t. So therefore, you want to determine the order, you must look at the highest derivative in terms of y. So that's order is 2. So therefore, the order of this equation is 2. And therefore, you want to look at, is it linear or nonlinear equation? Well, you look at t squared, right? So t squared is the coefficient of y double prime. It's okay because this coefficient does not depend on y. And what about 5? 5 is the coefficient in front of y. This is the coefficient independent of y. And this tangent of t, this is what we call it the right-hand side. Right? But it is more exactly to say that this is the term that do not involve any of those y's, and it is not a nonlinear function. So therefore, it's linear, right? This equation is linear. And when we say homogeneous, you should say no, because it's a non-homogeneous equation. That means there is we say non-zero right-hand side, but it's more precise to say there is a non-zero term that do not depend on any of those y's. So that's no. Okay. Now let's look at the last equation. Let's see, this time I will finish everything. Okay, so of course, this is a function y in terms of t, right? So because you have t squared y double prime minus 4 times t y prime plus 4y. So y in terms of t, the highest derivative is 2, right? So, and this is a linear equation because this coefficient t squared is independent of the y double prime y, and 4t is another function independent of y, and 4 is a function independent of y. So that's the yes. Okay, this is a linear equation. Is it homogeneous or non-homogeneous? Well, we can say there's 0 right-hand side, but you can, it's more precise to say that this equation has no term that does not have a term that does not depend on any of those y's. So therefore, it is a homogeneous equation. Okay, so this is kind of a typical style of our future lectures. And we're going to practice together a lot of questions. I think you're doing a wonderful job in answering my questions. Okay, so, and I appreciate it. Okay, so here, let me spend like 10 more minutes. Okay, so 10 more minutes for a real world exercise. Okay, so here's a practice exercise that from spring semester 2015, exam 1, problem number 1. Okay, so let's say spring semester. Okay, so as you can see, this is how your initial exam. Okay, so our first exam is coming up soon, within 1 month, right? So this is how your exam is going to look like. And there are instructions. This exam has 5 problems. You have 50 minutes to finish it, right? So the sum is 100. And look at the first question. Okay, so you can see that this is worth 16 points. So it's just 8 blanks and worth 16 points, right? So the question asks you, classify each of these differential equations. Okay, so here's one important tip for participating in exams, is that you must look at instructions carefully. Okay, so please try to look at the instructions on the problems and on the exam carefully. Understand what it is asking for, right? So here it says, can you classify each differential equation by completing the columns, right? So, and classify it. So let's work together and quickly. Okay, so is this a function y in terms of x, or it is of x in terms of y? Anybody can answer this question? Y in terms of x or x in terms of y? Anyone has idea? Want to hear from you.
X in terms of y.
X in terms of y, right? So that's kind of, you must be very careful. You see, on the exams, they're not going to be so straightforward. They're not going to just give you y in terms of x, but it is x in terms of y. But it doesn't matter. The highest derivative of x up here is 5. So the order must be 5. Is this a linear equation or nonlinear equation? How do we determine that? Well, as I said, since it is x in terms of y, you must look at the coefficients in front of x and x derivatives, right? So that, for example, here, x to the 5th derivative has a coefficient 1. X to the 1st derivative has coefficient y, 2y cubed. It doesn't depend on x, and x has a coefficient -6. It doesn't depend on x. So everything is fine. It must be a linear equation. Can you tell me it's a homogeneous or non-homogeneous equation? Anybody has idea? This is a little bit more challenging, but I would appreciate a lot if you can try that. Is it a homogeneous or non-homogeneous equation? Anybody has idea? Well, in order to determine homogeneous or non-homogeneous, you must see, I mean, there is a right-hand side. Does it mean it's non-homogeneous or homogeneous? Anybody has idea? Want to hear from you. Anyone has idea?
It's non-homogeneous because it's not 0.
Non-homogeneous because the right hand. But remember, when I say the right hand side is just relative. right? So you can move the right-hand side to the left. It doesn't really matter. You must not just determine everything from this so-called right-hand, but rather the feature is that it must be some term that do not depend on any of those y's. There are some term that's completely free that does not have any of those y's. It just have the t. So in a particular question that we have here, that means you're looking for some term that do not depend on any of those x's, just depend on y. Do you have such a term? You do not have such a term, right? So the right-hand side is very relative. You can move this term to the left, you can move this term to the left, then you can see there's no term that do not depend on any of those. There's no term that do not depend on x, right? Because x is the function, like what happened here. You must look for a term that do not depend on the y. That means you must look for a term that do not depend on any of those unknown functions. But here you can see that you do not have such a term. All the terms depend on unknown function, which you just answered me. The unknown function is x. So therefore, this equation is really homogeneous. Okay, so I understand. I mean, it doesn't matter that you're making small errors here. I would strongly encourage you to answer my questions. And this is very natural. Okay, so I can tell you that for 90% or 95% of beginners, they're going to make errors in this kind of questions. Okay, it's kind of very confusing for beginners. That's why I encourage you. Okay, so one of the advantages of doing online classes is that you're going to see the video even after the lecture. So I would encourage you to work on it by yourself again and again until you get the essence of the understanding of how to tell the difference between linear, nonlinear, homogeneous, non-homogeneous. So this is actually, I can tell you, it's a homogeneous equation. Okay, so that's kind of correct. That's kind of anti-intuitive, but it is indeed homogeneous. Okay, so let's look at this equation. Okay, so let's be a little bit faster. Is it u in terms of v or v in terms of u? Anybody has idea? Want to hear from you. Is it u in terms of v or v in terms of u? Anyone has idea? U in terms of v or v in terms of u? Anybody has idea?
V in terms of u.
Yeah, it's v in terms of u, right? So that's for you look at highest derivative of v, that's 2. So that means this is a second order equation. Now we're going to see, is it linear, nonlinear equation? What should we see? Well, we should want to look at the derivative, the coefficients in front of v and derivatives. This coefficient is good, it doesn't depend on v. This coefficient is y, it doesn't depend on v, but you are going to see a v square here. This is not what we want to look at, right? So as long as you see v square, it means it's a nonlinear equation, right? Like what you see before. You never see y derivative square or any square root or any kind of such nonlinear operation. So therefore, this is a nonlinear equation. And if it's a nonlinear equation, it makes no sense to answer is it homogeneous or non-homogeneous or such questions, right? So now let's quickly look at this equation. Can you tell me, is it y in terms of p or p in terms of y? Anybody has idea? Y in terms of p or p in terms of y? Anyone has idea?
P in terms of y.
P in terms of y, right? So thank you very much. So you see that the questions can be very flexible, right? So y in one equation can be the function, in another equation maybe the variable, right? So you must be very flexible with this. And you are absolutely right. This is P in terms of y. If it is P in terms of y, the order is just 1 because the highest derivative of P is just the first order, so that's order is 1. Is this a linear or nonlinear equation? How do we determine that? Well, you look at the coefficients in front of P, this is a function of y, but then you look at the coefficient in front of P prime, you see a P prime square. And if you square the P prime, it means you create a nonlinearity. So that's a nonlinear equation, and you don't have to answer whether or not it's homogeneous or non-homogeneous. If they ask you, you say not applicable. Okay, so now let's look at this equation. Okay, last practice exercise. Can you tell me it is W in terms of R or R in terms of W? Which one? Anyone has an idea? Is it W
in terms of R?
It's W in terms of R, right? So absolutely right. Right. Thank you very much, right? So this is indeed right. So it's looking for W in terms of R. So therefore, you just want to look at the derivative of W. The highest derivative W that occurs in this equation is 1. So that means the order is 1. Is this a linear equation or nonlinear equation? So can anybody tell me about this? How do we check that? Well, as long as we see the W, we have to look at the coefficients of W. Therefore, this r cosine r is a function, but this is somebody says this is a nonlinear equation of r. It doesn't matter. It does not. It just suffices that this term do not depend on w. Right, this term does not involve any of those w, so it's completely fine. What about this -1? Well, this -1, of course, is a function independent of w, and the 3 is something that even independent of w as well as the r, right? So that's kind of, this is a linear equation, not a problem. It just fits in this general form of ODEs in the sense that the coefficients are r cosine r and -1. Now the question here to ask is that, is this a homogeneous or non-homogeneous? It is a linear equation. Therefore, we want to see if it is a homogeneous or non-homogeneous equation. Anybody can give me the answer? So this time I want to hear from you. So can you tell me, is this a homogeneous or non-homogeneous equation? Anybody has the idea?
Non-homogeneous.
Non-homogeneous, right? So what's your reason? Well, the reason is that there is a 3. You might just simply say, well, I have a non-zero term here. But what happens if I move this term to the left? I say it's r cosine r w prime minus w minus 3, 0. It's still non-homogeneous because you have a term 3 that do not depend on r as well as the w, right? So that there does not, the 3 that do not depend, sorry. So the 3 may depend, it can be 3r, it's completely fine. But there is a term that do not depend on w. Right, so if there's a term do not depend on any of those unknown variables, then if this term is non-zero, then this is a so-called non-homogeneous equation. So this is a kind of very important to realize this. And I understand that you might be feel very confused the first time when you're working through these kind of examples. But it doesn't matter. The advantage of doing an online class is that we have recorded all our lectures. Therefore, I would suggest to urge you to take a look back into it and watch carefully and understand by heart. Okay, so I can guarantee you that this will be your exam problem. Okay, so I mean not exactly this problem, but problem of this kind is going to happen on your first exam. There's going to be such a table, ask you to fill in, is this an order of this equation, linear or nonlinear? Okay, so that's kind of the thing I want to say for classification of ordinary differential equation, very important. Okay, let me take the final 3 minutes to finish this chapter about the solution of an ordinary differential equation. So for the rest of those lectures, we're going to talk about how to solve ordinary differential equation, and therefore we have to understand what's the solution of an ordinary differential equation. By in what sense are we going to say that I have a solution of this equation? Well, by solution, it's just follows this definition. It just says that a solution of ODE is an open interval on an open interval AI, such is a function. So basically, solution is a function that on certain interval satisfies the ODE. By satisfying this ODE, it means that you plug in this function, you plug in any necessary derivative of this function back into the equation, it is going to result in a 0 and going to an equality, which is kind of a even tautological notion, right? So it's kind of tautological to understand this. So just to show you one exercise that might give you the meaning of this problem, right? So this problem says that, can you determine the value of the constant r for which such a differential equation has the solutions of the form t to the power of r for t positive? Okay, so how do you determine that? Well, you have the form of the solution is t to the power of r. You just don't know what's the choice of r, but you know the equation as we just said. By solution of differential equation, it means that you just take all these derivatives, put back into the equation, it should be an equality. So that's very simple exercise is that you just put t to the power of r there, you take derivative, first derivative is r t to the power r minus 1, second derivative is r minus 1 t to the power r minus 2, you put everything back into this differential equation. Then you're going to raise something like this, t to the square r minus 1 t to the r minus 2 minus 4tr t to the r minus 1 plus 4tr power is equal to 0. You're going to tidy everything up, right? So you're going to clean and tidy everything up. Then I'm not going to do much for this exercise. It's a very simple and straightforward exercise. You end up in an equation saying that t to the power of r multiplied by this quadratic equation r is equal to 0. So what does it really tell you? Well, remember, t is arbitrary, right? So here t is for any t positive, so you cannot guarantee, you can guarantee that t to the power of r is not going to be 0. So therefore, the coefficient here must be equal to 0, which means that r squared minus 5 times r plus 4 is equal to 0, and you get the solution r is either equal to 1 or equal to 4, because you can factorize this quadratic formula, right? So you can factorize this quadratic form. You get the solution r is equal to 4, 1, or r equal to 4. So therefore, the solutions of this equation is simply t or t to the power of 4. Okay, so this is a very simple and straightforward exercise. We won't put much time on it, but it actually tells us, okay, it actually tells us what is the meaning of a differential equation, right? So, I mean, what's the meaning of the solution of an ODE? It is just a function that satisfies the whole equation. Okay, so that's kind of we have completely finished the chapter for our first chapter, and starting from next lecture, we're going to come back to the second chapter. Okay, so that's